hold on to your hats because this module is going to take a while in time. So I want to encourage you. I'm going to throw a lot of material at you. It's all very much related to one another, so I couldn't bust up the material into multiple videos. So if you do get hung up or get confused, do not, of course, don't hesitate to go back and replay, pause, whatever you need to do to really learn this material because it's going to be the foundation for success for chapter 3 and for the rest of this class. So let's go ahead and get started. This particular video is all about what we call PVT surfaces and learning about phases, the detailed names of phases. And you also see even that I've labeled this particular video as hard. So please hang in there, absorb what you can, and I'm hoping to show you some things so that you're going to be able to get started doing your homework that's assigned to you regarding identifying phases and then determining properties from thermodynamic property tables. Okay, so let's see. Phases you already know. So right out of Common Sense 101, we've covered in the previous video. Let's say, this is all relative to H2O, isn't it? You look at this with your eyes, that would be, ice would be the solid phase. This bucket of water, you'd know it as the liquid phase. It's a bucket full of liquid water. But on the stove, if you took that exact water and you put it on the stove, added heat, you're going to get some mixture. It's a boiling mixture of liquid and vapor. You've observed this, okay? And then finally, the vapor phase that I've tried to depict with this steam coming out of the bottom of a vessel through some valves and some piping. Now, that's not the end of the story. There's a few more phases that engineers need to learn and cover. But I do want to make you feel better. There's a lot of things you know simply using your own Common Sense 101 already. So you're already prepared to learn a little bit more. A little screenshot from your book, and it says evaluating properties, general considerations. So I do want to chase you to section 3.2.1, which introduces what's called the pressure, specific volume, temperature, surface. So this is like a XYZ plot, and I'm going to blow that up on the next slide. And then further in the textbook, section 3.2.2 says projections of the PVT surface, because we as engineers typically, when we're graphing things on pencil and paper, we don't draw three-dimensional sketches. We pretty much draw two-dimensional sketches, or in other words, two coordinates at a time out of those three. So that's what's coming ahead. Do let me try to reference your textbook. That's really it is a nice and detailed description of what you're going to cover. What I'm going to try to hit the high points on in this video. And even the video is going to take a long time. So this is the three-dimensional surface properties for pressure, specific volume, and temperature. And so let's look at what we've got here. It says the numerical values for each axis depend on the substance. And so this three-dimensional plot is going to be slightly different depending on the substance you have. And so this one in particular would be a three-dimensional plot for H2O. Let's look at the basics. It's three dimensions. It's kind of like X, Y, Z. And so one axis is pressure, P. That's the vertical axis. The horizontal axis would be specific volume, little v. And kind of like the Z axis is temperature. And so what I want to remind you is sometimes it's hard for me even to visualize is that these dots, there'd be a bunch of dots that lay on this swoopy down surface, these various surfaces. Some are steep, some are not so steep. They're different colors of blue, but recognize that all these colors of blue represent a three-dimensional surface. Okay. One thing that's covered here is critical point. Do you remember a mention of a critical point in high school chemistry, in college chemistry? That would be, it's a combination of a temperature and a pressure that describes the critical point. And typically, well, we'll learn more about what the critical point means a little later, so I don't want to get ahead of myself. Also, there's a triple point you may have been exposed to in high school, right? I don't remember a whole lot about the triple point, and I will tell you that the triple point is a it is a very low, look how, see that it's a low pressure, and this little green line could represent, it says constant pressure line. That line could represent 1 atmosphere. And so this triple point is a pressure that's much lower than an atmosphere. But it is, for water, I remember that the triple point temperature is right about at the freezing point. We won't get down in the weeds on that, but do recognize that this three-dimensional plot, obviously it's an infinite number of points or states that lay on the blue surface. So here we go. I'm going to try to get you a little more familiar with it. This is going to be qualitative, and then we're going to get into something qualitative here in a few minutes. Quantitative first. Qualitative first, excuse me. We're going to go through a mental exercise, and I'm going to guide you through this. For H2O, and let's say that we're interested in simply saying what these yellow dots are. I've picked out a set of 7 dots that are laying on this three-dimensional surface, and they all happen to be laying on a line of constant pressure. So you have to imagine in your head taking a horizontal slice, a plane, P-L-A-N-E, through P equals 1 atmosphere, 14.7 psi. 101 kPa. So imagine slicing through this three-dimensional plot, and we're gonna talk about 7 yellow dots that lay on that constant pressure line. Hope that's what we're going to look at. So let's step through what would we call the phase of each of these dots. And hopefully you're studying the three-dimensional plot and you see some words: solid, liquid, solid and vapor, liquid and vapor, and gas. See those? That does describe in words the phase of these different colors of blue. So here we go. Okay, the first situation, the first dot, situation 1, that dot is laying on this darker blue called solid, so that's ice. Okay, I got it. Let's look ahead. Let's look at where we're going next. Next yellow dot. Well, that next yellow dot is laying on another blue surface here. It took a little bit of a dog leg, almost like a fold, and it's laying on the solid and liquid line. So that second dot would be a mixture of ice and water. That would be a lot like cubes of ice floating around in ice water. That's what that would be like. Next one, next example, next situation. Now we're on a little lighter blue here that just says liquid. Now the technical name of this area is called compressed liquid, and you're going to have to commit that to memory instead of just liquid. Another way to call it is subcooled liquid. And also the common name for this area would be tap water. Tap water. All right. Just plain old liquid tap water. That's what situation 3 is all about. Now, we continue. And what are we doing with temperature? Notice what our temperature is doing as we're moving from left to right. Look at that. Look at this z-axis. Temperature is increasing as we're moving to the next one. So let's see where the next one leads us, the next situation. Situation 4, we're continuing to increase the temperature of our situation to now we've reached the boiling point of water. And so I would call this point right here, I'd call that scalding water. If there's water on the stove and it's just reached the boiling point and you stuck your hand in it, you know you're going to get burned. That is scalding water. Another thing to point out, notice how this little kind of intermediate blue represents a little bit of a dome. So see what a kind of a crazy shape that is. It's not a rectangle. It's kind of like a dome shape. All right, we covered situation 4. Now notice here, now we're coming over to this next yellow dot, but the temperature isn't changing, but we're in a different phase. Okay. And so that phase is, so the temperature's not changing, pressure's still the same. This is like where we're boiling water on the stove, and I would call situation 5 a saturated mixture of steam and water. Visualization is what's on your stove boiling. Okay. Now we're going to continue on. We're going to continue to boil that water. And we're going to go to our next situation. We're boiling at constant pressure. And the temperature hasn't changed. So I hope that you know that when you boil water on the stove, no matter how much you boil it, that temperature isn't getting any bigger. The temperature is not, once you reach the boiling point on the stove, you can't make it any hotter than the boiling point on the stove. It's a very interesting part of boiling things. Situation 6, though, is we've continued to boil it, and all the water has turned into vapor. Okay. So that's called saturated vapor or saturated steam. In engineering, we call that saturated vapor. That's this situation right here. And notice how it's laying on this dome, on the right-hand part of the dome. When your dot is laying on that part, that's called saturated vapor. But now we're going to continue to heat. We're going to continue to add heat to that saturated vapor. That's something we can't do on the stove, but we continue to heat it at constant pressure. And now we're over into this new phase, this light blue phase, and that's called superheated vapor. And that is important for this class. So recognize when you continue to heat water, that you continue to heat steam, add more and more heat to it, you can actually reach a higher temperature than the boiling point temperature, and that's called superheated vapor. That is an important point to make. Situation 7, superheated vapor. I hope working through those 7 examples has been worth the time. If you're confused, play it back and try to get comfortable with this 7 situation exercise. Okay, this is a little bit of a recap of the phases of H2O that we just identified in our example. Solid, liquid and solid, compressed liquid, saturated liquid vapor, saturated vapor, and then superheated vapor. So that's 1, 2, 3, 4, 5, 6, 7 phases that you're going to need to commit to memory. There are other phase change substances other than just good old H2O, and those would be refrigerant, things like ammonia and R134A, and both of these would be considered refrigerants. R134A would be the type of refrigerant you have in your home air conditioning system, for example. Another phase change substance would be propane. For those of you that have a gas grill, you're kind of familiar with bottles of propane. And there are other substances, of course, that can change phases. Okay, I hope this slide helps you relate your familiar understanding of phases back to the technical name for phases. Okay, we're getting somewhere, and we're getting closer to quantifying things. But what I want to do now is work you through how the textbook generates and how we're going to be using in this course nearly through the rest of the class what we call a PV diagram, or a pressure specific volume diagram. Now, think back about some of your homework. For closed systems that you had, didn't you draw a pressure volume diagram already for some homework problems? We're going to be generating that, but for phase change substances, we're going to add a little complexity to the PV diagrams you've been drawing. So let me see if I can introduce this idea to you. Let's take this 3-dimensional surface, and I want you to imagine eyeballing the surface by looking down, taking a side view, so that all you can see, so I'm trying to get over here and look, all you can see is the pressure axis and the specific volume axis, and you can't see that 3rd dimension of the temperature axis. Try Try to imagine that in your mind, taking a side view of this three-dimensional surface. Ugh, what would that look like graphically in 2 dimensions? Okay, here is what graphically that side view looks like. So I've tried to show that if you take this three-dimensional surface in side view, what you're going to see is a pressure and specific volume set of axes in the X and the Y, and you're going to see a bunch of lines of constant temperature. Lines of constant temperature. So all these blue lines and then this purple line represent lines where the temperature is constant. So you have to imagine going in with a Sharpie and drawing in lines where temperature is constant on this three-dimensional surface, and then you'll see in side view those lines that you drew with the Sharpie will appear on the 2-dimensional view. I hope that helps, but you're going to need to commit to memory what this pressure specific volume diagram looks like, and I've got a lot more details about that. Let me go to the next slide before jabbering on about what this PV diagram for phase change substance looks like. Yes, thought I remembered I had that. So I need to ask you to try to develop as quickly as you can how to identify phases on this pressure specific volume diagram. So let's dissect this look. We've got X and Y axes. The Y axis is pressure. X axis is specific volume. So one thing you see immediately is this green line. That's called the vapor dome. Okay, commit that to memory. This green line, the vapor dome. Okay, it's not perfectly symmetrical and it depends on the substance, but do understand that's called the vapor dome, in common with all substances that can change their phases. Here's the critical point. It's the point where this dome has a maximum value. So do you see that this pressure right here would be considered the critical pressure? And this specific volume here, whatever that number is, would be called the critical specific volume. And this line of constant temperature, this purple line, would be called the critical temperature. All right, so below this critical pressure, if you're laying anywhere, if your X and Y, if your P and V lies anywhere below the critical pressure, critical point, you need to train yourself to be able to say, I know what phase I'm at depending on where I am relative to the vapor dome. Okay, so I hope you've been studying it while I've been jabbering. When you're on the left-hand side of this vapor dome, you are a saturated liquid. That would be like water right at the boiling point. It's no steam yet, water at the boiling point. When you're laying on this side of the vapor dome, you're what's called saturated vapor. That's where you've got water's been boiling and boiling and boiling, and all the water's boiled away. It maybe escaped to the surroundings, okay? And all that's left is saturated vapor. You can't even see it with your eyes. It's saturated vapor at the boiling point temperature. If you're to the right of this vapor dome, you're superheated vapor. Now, that's very important for us engineers who are trying to, let's say, make electric power in a steam power plant, when we're trying to use steam to accomplish some heating objective, things like that. So to the right of this vapor dome is superheated vapor. That's the phase. If you're under the dome, you're a saturated mixture. In other words, the visibility there is like that Pyrex pot on the stove in which you can see with your eyes a mix of liquid and bubbling up saturated vapor. It's a mixture of saturated liquid and saturated vapor, and in this class we call that a saturated mixture. Oh, I've labeled, if you're sitting on this leg, this green part, the right-hand side of the dome, typically we use a subscript G. That'd be kind of like, maybe think of gas, maybe. So the G subscript applies if you're laying on the right-hand side of this dome. If you're saturated liquid, the subscript F, maybe fluid, maybe, but F is is the subscript that represents you're laying on this left-hand side of the vapor dome. So one last thing I need to cover is what's called compressed liquid. That's to the left of the vapor dome. And compressed liquid, I want you to think about in your mind, compressed liquid is like tap water. Wouldn't you say tap water is not boiling, is it? It's at 1 atmosphere. You pull it out of the tap and put it in a bucket. The pressure of that water is 1 atmosphere. It's not boiling. It's tap water, and it's called a compressed liquid. So try to get that in your head. Okay, so now we're going to do a mental exercise to start quantifying. We're interested in studying H2O, and what we'd like to do, here's what I want to do. I want to, for T3 equals 100 degrees C. So see, here is a blue line. I'm going to trace it with my cursor. Here's a line of constant temperature, T3. So what I'm tracing with my cursor is a constant temperature line, and we're interested in 100 degrees C. And the exercise we're going to do is, what's the pressure? What's this pressure on the PV diagram and the vapor dome? What is this pressure for a water temperature of 100 degrees C? Oh, I've looked up the critical temperature is 374 degrees C. But for 100 degrees C, what's the pressure? Huh? Anybody have an idea? How about common sense? What's the boiling point of water on the stove? It's 100 degrees C. I learned that in high school. Okay, 100 degrees C. So on the stove, the boiling point's 100 degrees. What's the pressure of water on the stove? It's 1 atmosphere. So we're going to be able to look it up, but my intuition tells me that P3 is about 101 kPa or 14.7 psi absolute or 1 atmosphere. And also we want to figure out numerically what is the specific volume VG3, T3 is 100 degrees C, okay, and what's VF3. So we're going to go through this numerical exercise. You're going to be doing this over and over and over again in this class. 3 things. What's P3? What's VG3? And what's VF3 in numbers and units? Okay, so I've taken a screenshot out of the book to kind of get you started. All right. So what's our answer? Well, we're going to go to the back of the book and we're going to work in SI units because we got a temperature of 100 degrees C and we've got H2O. So we'll thumb back. Oh, here we go. Properties of saturated water. That's what we're interested in. Liquids and vapors. Yes, we're under the dome. Saturated water. Keyword water. Okay, got it. And we're going to go to something called temperature table because we have the temperature. That's kind of a no-brainer, right? So let's look and see what we have. The left column labels temperatures. All right. Well, here is 100 degrees C. Good. I'm going to circle what I need. The next column says pressure in bars. Pressure in bars. Ugh. Okay. But you see that we're going to get an immediate answer because at 100 degrees C, the saturation pressure, this pressure temperature pair represents the 2 dependent variables that describes the boiling point in temperature and pressure. So at a temperature of 100 degrees C, the pressure is 1.014 bar. So I've written it down and I'm immediately changing it to kPa because in most of my homework problems, I need to be working in kPa. So the pressure, PG3, is 101.4 kPa. So I can label that on my PV diagram. Okay, so now, do you see, another thing to point out is, do you see at different pressures, if you go to a different pressure, maybe like a pressure cooker, okay, if you're able to generate a larger pressure on the stove, let's say 270 kPa, do you see that water's going to boil at 130 degrees C? So that's what this properties table what that buys you as an engineer. So for any pressure, you can look up the boiling point temperature, and vice versa. For any temperature, you can look up the pressure that needs to be in order to boil. All right. We're assigned also to write down VF3 and VG3. Let's work on VF first. In other words, the specific volume of saturated liquid. Let's look at that column heading, VF times 10 to the cubed. Oh, okay. How do I? So I don't write down 1.0435. I don't write that down. This is a little tricky on this temperature table. For saturated liquid, I've got to move this number's decimal place 3 places to the left. So VF3 is the number 0.001035 cubic meters per kilogram. So that's what I'm going to write down. Now VG3, okay, look at that. Here's VG for saturated vapor. So the table can be your friend if you understand these column headings, and I just have to write down 1.673 cubic meters per kilogram. So we have quantified, we've done the first job of quantifying for water at a temperature of 100 degrees C. What's the pressure is it boiling at, and what's VG3 and VF3? Okay, so here's what we need to do to finish. If that were a homework problem, we would label our PV diagram. Here's our green vapor dome. We just looked up these numbers in the temperature table because we had the temperature. And so we've got 101.4 kPa is the pressure, and this VF3 is this tiny little number, and VG3 is 1.673 cubic meters per kilogram. And then check, we got it. Now, if you're asked, what is the density of saturated liquid water at 100 degrees C? What's the density? All right. Well, we just found the specific volume is this tiny number. The density is the reciprocal of the specific volume. And so the density is 958.3 kilograms per cubic meter. And that makes some common sense, right? Because you were taught in high school that the nominal density of water is about 1,000 kilograms per cubic meter, right? You remember that? 1,000 kilograms per cubic meter is the nominal density of water. So we are absolutely on the right track here. Some live lookup demos. Let me try to stop sharing. And hold on. I need to minimize me. Hold on here. Let me go back to share. I've made a big, so I apologize. I've got to hit escape, not stop sharing. And I need to go, and I'm going to go to my Steam tables. This is what we were just looking at in screenshots here. Temperature table. So notice here, here's our left column heading temperature, pressure, the saturation pressure, corresponding to temperature, and we're getting better at looking up specific volume values. I'm going to scroll down. The temperatures just get higher and higher. Here's table A2 continued. But now what I'd like to do is show the next table up is the pressure table. And let's look with our eyes. What's the difference between the pressure table and the temperature table? The difference is in the left column heading, the left columns. Notice here how the pressure is tabulated in the left column, the pressure, and let's pick off this one. 1 bar, that's 100 kPa. And let's look at the corresponding temperature. In other words, T sub G, the boiling point temperature at 100 kPa. It's 99.63. So do you see that that sort of makes sense? So this pressure table is identical to the temperature table other than the way that the columns are arranged and therefore the way the numbers shake out for these different properties. And so do you see here, saturated liquid, V sub F times 10 cubed is 1.04. So you've got that, you're going to slip those decimal place 3 places. 1.694. These numbers are nearly identical to what we looked at in the temperature table, except we're only off by, our pressure is only off by a little fraction, right? So 1 bar is almost 1 atmosphere. So you get the idea. Pressure table and temperature table, very similar. Let me see if I can go down to English units quickly. And again, you're going to have to just excuse me for goofing around here. And here we are in the English temperature table. I found it. Left column, temperature. Next column, pressure. Notice here the units are different. Degrees F and PSI, pounds per square inch. Okay. We don't have that dilemma. Our units, cubic feet per pound mass for specific volume. And we don't have that dilemma of that 10 cubed business here. Okay. So that's a nice part. That's one of the advantages of the English system. All right. So we have a temperature table in the English system. We'll scroll down. Temperatures get hotter and hotter and hotter. Well, here, let's look at 212. You know that water boils at 212 degrees on the stove, degrees F. Well, look at the pressure, 14.70. That's the saturation pressure at the boiling point. And so I hope you get the same idea here. So you get the relationship between T sub G and P sub G in these saturated tables. I'm going to scroll down to the pressure table, saturated water, liquid vapor, pressure table. Well, let's see. Let's look for 1 atmosphere. Oh, look at this. How nice. 14.7 PSI, boiling point temperature, 212. And we get similar numbers for the specific volume lookup. And so I do want to get you sort of comfortable with the similarities in our saturated water, saturated liquid vapor phase, temperature table and pressure table. It's simply a convenience on if you have pressure given or if you have temperature given. Okay, so hopefully I can get back to PowerPoint and continue my work. Okay, so let's see what we have. So, next. That was the PV diagrams. That was a time spent on what's the pressure volume diagram, pressure specific volume diagram, vapor dome. Okay. It is my hope that you're going to use the PV diagram for vapor domes for phase change substances the most. But here's another type of diagram that your instructor may be getting to use as well. What about looking down on this 3-dimensional plot? If you look down on it, do you see that you're not going to be able to see the pressure axis? You're going to see temperature axis and specific volume axis. So if you're looking down, here's what you'll see. You're also going to see a dome, okay? And here's your critical point. And you're going to see a dome that's much, much steeper here to the left and a lot less steep on the right. And so you're going to have temperature on the y-axis, specific volume on the x. And now I'm going to go a little faster because the point to make here is you still need to be able to say what your phases are on the TV diagram. If you're under the dome, so it's a little different shaped dome because you're looking at a different view, but when you're under the dome, you're a saturated mixture. When you're on the dome to the right, you're a saturated vapor. When you're on the dome, on the left-hand side, you're a saturated liquid right there at the boiling point, okay? And if you're to the left of the dome, you're a compressed liquid. That's like tap water. So try to get, I'm starting to blaze through this, but that's the way you generate the TV diagrams. Both the PV and the TV diagrams are generated from that 3-dimensional surface. There's a fun fact that I'm going to blaze through, and that is that ice floats in water. And that's an important fact for us living on the earth. This is a fun fact, okay? So if we went through if we went to the temperature table for water. And we looked up V sub F. V sub F, that's the specific volume of saturated liquid. You're going to get a number of different results, okay? And you're going to tabulate these numbers against temperature. So 0.01 degrees C. Wow, that's at an atmosphere, that's the freezing point, isn't it? That's where ice forms. At minus 20 and minus 30, you've got ice, okay? And so you get a different value for specific volume. If you take the reciprocal of that and calculate density, look what's happening to density of H2O as it becomes ice. It's becoming less and less dense. And so you can look this up in the back of your book for liquid and solid table. So what's the conclusion? As ice gets colder and colder, it floats in water. Ice always floats in water because it's always less dense than water. And the neat thing about that, so here's on your counter, you observe this. In the ocean, you observe this. So this natural phenomenon of H2O prevents oceans from becoming a big block of ice. And that would be bad news for us. If the ocean, we probably never would have been invented if the oceans became one big block of ice and not water. So we're fortunate that for H2O, ice floats. There's a downside to ice being less dense or a bigger specific volume than water, isn't there? For those of you who are homeowners or have rented property, and it's in very cold weather, you may have experienced copper pipes bursting when the water inside the copper freezes. So that's a real downside of ice expanding as it gets colder and becomes ice from water. Wow, so this is a hard part. How can I keep all these details straight? I have thrown a lot of details at you in a small amount of time. Okay. So here's what I want you to think about. I want to try to help you keep it simple. And so one thing is, in this class, you're going to find that we're not going to be dealing much with ice, very little with ice. It all depends on your instructor, but don't expect to be spending much time on the solid phases. So you're going to have to worry about the following phases: compressed liquids, in other words, tap water, boiler feed water. Okay. Saturated liquid. Think of that as water at the boiling point. So in other words, how do you relate these technical terms to things you already know? Saturated liquid vapor mixture. Think of that as boiling water on the stove, something you can see. A saturated vapor. Well, that's steam at the boiling point. Think of that from that pipe that's spewing out steam. Okay. And then superheated vapor, that's something I've just explained to you that we call superheated steam. It's steam that's heated even higher temperature than steam at the boiling point. That's superheated vapor. And now I'm going to draw a line because further in Chapter 3, you're going to be dealing with gases. So this part up here is substances that can change phase, like H2O. I've drawn a red line, and then further in the chapter, we're going to study gases, and that's going to be things like air, carbon dioxide, nitrogen, and other commonly recognized gases. So I'm trying to help you categorize in your head how to identify different substances. Phase change substance, that's what we're talking about now. Later on, I recognize that as a gas. It's going to be a little different set of skills. There's a video that I really suggest that you watch. In my example problems STEAM playlist, if you can fish out property evaluation demo, it's a 30-minute video, and it's going to show you step by step how to determine the phase of a substance, phase change substance like H2O, refrigerant, and propane. Some example problems worked out start to finish. And it shows you how to determine a needed property when you have a pair of properties given to you. Some supporting videos, also in the example problems STEAM playlist. I have 3 videos regarding learning a little bit more, becoming more comfortable with the vapor dome, particularly the PV diagram, the vapor dome, the PV diagram. You might be interested in a 30-minute video on what I call how to boil water. And I just brought my webcam down to the stove and put some water on the stove, actually in a teapot, in a Pyrex teapot, and show how to boil the water. And so it illustrates compressed liquid. I start with tap water. I just add heat to it from the stove. It becomes saturated liquid, and it reaches boiling point, and it just continues to sit there and boil and boil and boil. Have a look. So we have reached, mercifully, the end of this video. And so let's see. I've shown you the PVT surface. The most important thing is getting a feel for drawing in pencil and paper the pressure-specific volume diagram for a phase-change substance, getting practice with H2O. I've tried to give you a little teaser or a little sampler of how do you quantify properties. We looked at, given a certain temperature of H2O, at what pressure does it boil at? Okay. And also I showed you how to look up V sub G and V sub F, okay, using the pressure table or the temperature table. Either can work, depending on whether you have the pressure or have the temperature. And then finally, the TV diagram, the temperature-specific volume diagram for phase-change substance that your instructor may or may not have you use. I got to tell you that in my class, I nearly totally depend on the PV diagram for some good subtle reasons, and I do that to try to keep it simple. So the next video up is we're going to add another difficult thing to understand, what's called the steam or the quality of a saturated mixture. And then beyond that, after another few videos, we're going to cover how to deal with properties of gases. So that's further on down the stream. Whew. I hope that helps you get started understanding about how to quantify properties associated with phase change substances. The key is some practice in drawing the pressure volume diagram. Start by drawing your axes, then draw in a dome, and then draw in some lines of constant temperature. And you're only going to get good at this by practice, practice, practice. So hope that helps. Try tackling those homework problems that you're assigned in Chapter 3, and good luck with that.